The Maxtrudder foundation pile formwork and precast production system enables efficient, high-quality manufacturing of prefabricated foundation piles. The production process begins with automated reinforcement cage placement, followed by formwork positioning and precision concrete pouring, using vibration compaction to ensure density and durability. Designed for durability and precision, the system supports a wide range of pile cross-sections and lengths, suitable for residential, commercial, and industrial foundations. The modular setup allows users to tailor the level of automation and design. Key benefits include rapid installation without excavation, compatibility with various soil types, and immediate load-bearing capability post-installation. With factory-cured concrete, construction proceeds without delays or weather constraints. A Rodbuster, also known as a reinforcing ironworker, is responsible for placing and securing steel reinforcing bars, rebar, within concrete forms prior to pouring. Using tools such as pliers, tie wire reels, and cutting torches, the Rodbuster bends, cuts, and ties rebar according to detailed construction blueprints and placement schedules. Safety is critical, as tasks are often performed at heights or within congested rebar assemblies. Precision in spacing, alignment, and anchorage is essential to ensure structural integrity and compliance with building codes. By July 2011, excavation of the Tokamac building was complete. Blinding concrete works totaled 550 cubic meters, with 250 m³ remaining. Reinforcement of the lower basemat and walls began, using 3,400 tons of steel in 2 layers. The next milestone pouring the first Tokamac basemat concrete. The Yufelli Dam and Yufelli hydroelectric power plant construction project is supported by high-capacity production and transportation infrastructure. A 1,100 tons per hour capacity crushing plant supplies the required aggregate for the dam works. The material is transported via an aggregate conveyor system to the batching facilities. The project includes concrete batching plants with capacities of 360 cubic meters per hour, 250 cubic meters per hour, and 195 cubic meters per hour, ensuring continuous concrete production. The freshly mixed concrete is delivered to the casting zones using a concrete conveyor line with a 200 cubic meters per hour transport capacity. This integrated system enables time-efficient operations and guarantees the production of high-volume, quality concrete. In complex hydroelectric construction projects like Yufelli, deploying such high-performance equipment across material processing and delivery lines is essential for maintaining progress and ensuring structural integrity. The combination of crushing, mixing, and conveying units reflects a coordinated engineering effort to meet demanding performance, durability, and schedule requirements in one of Turkey's most significant dam constructions. At Yufelli Dam, the body height has reached 73 meters. Once completed, with a height of 275 meters, it will become the tallest dam in its class worldwide. Embankment filling operations are continuing without interruption, marking steady progress toward this major engineering milestone in dam construction. Building concrete walls for an underground home involves precise shaping, structural reinforcement design, and measures to ensure long-term durability and resilience. First, excavation is completed to the desired depth, with footings poured to form a stable foundation. Formwork panels, modular steel or custom plywood, are then erected and securely reinforced to define the shape of the future walls. Inside these forms, steel reinforcing mesh is carefully installed to specifications to provide tensile strength and resist earth pressure. High-strength concrete is pumped into the forms in controlled lifts to ensure complete consolidation. Once cured, the forms are removed and the exterior surfaces of the concrete walls are thoroughly inspected. The steel panels are then removed by crane. The result is a strong, thermally efficient structure that supports the home while resisting horizontal loads from the surrounding soil and moisture. These concrete walls act as both foundation and living space in the underground design. The construction of the new Seilbahn Zugspitze marks a groundbreaking chapter in the history of the Bayerische Zugspitzbahn. Designed to access Germany's highest peak, the cable car sets 3 world records: greatest overall height difference, tallest steel support tower, and longest unsupported span. After 6 years of planning and construction, the project overcame extreme alpine conditions, including wind, snow, ice, and the geological complexity of the North Face. Initial works began in 2015 with crane installation and the setup of a materials ropeway. By summer 2017, the iconic 127-meter steel tower was completed in just 3 months. 4 153-ton support cables and 2 cabins followed, with a 10-week cable pulling operation. The old ABZ cable car, in service for nearly 55 years, was retired in April 2017. The new Seilbahn Zugspitze not only symbolizes engineering excellence under extreme constraints, but also significantly increases capacity and quality, with expectations of transporting over 1 million guests annually. Its completion stands as a proud and emotional achievement for all involved. Block molds offer an efficient solution for recycling surplus concrete into durable, stackable, interlocking blocks. Designed for ease of use, these molds enable rapid production of concrete blocks in various shapes and sizes. Their robust, flexible construction ensures long-term reliability, making them ideal for sustainable construction, retaining walls, or temporary structures. The Quay Bridge replacement project involved the rapid and coordinated removal and installation of a key railway overpass near Caldicot, Wales. This time-lapse sequence captures the operation executed over a strict 100-hour possession window on the South Wales Main Line. Preparatory works included constructing the new bridge structure offline adjacent to the railway while installing crane pads, temporary access roads, and jacking systems. Once the possession began, rail services were halted, and the existing bridge deck, consisting of concrete and steel, was carefully dismantled and lifted out using a 1,200-ton crawler crane. Subsequent to demolition, the bearing plinths and abutments were inspected and adjusted to precise tolerances. The prefabricated bridge unit, weighing several hundred tons, was then transported into position using self-propelled modular transporters, SPMTs. Guided by total station survey equipment, the structure was installed to within millimeter-level accuracy. Final works included stitching in the track bed, reconnecting signaling and cabling infrastructure, and completing waterproofing and parapet installation. Ballast was reinstated and tamping machines realigned the tracks for full operational clearance and safety assurance. Despite challenging weather and tight spatial constraints, the entire operation was completed on time and within specification. The time-lapse clearly illustrates the precision and efficiency required to execute a major bridge replacement in such a limited window, minimizing disruption to rail services and ensuring safety compliance throughout. The Gubris Tunnel, located north of Zurich, is a critical part of Switzerland's national motorway network. With its existing two-lane configuration accounting for a quarter of all traffic congestion hours on Swiss highways, the expansion to a 7-lane cross-section became one of the country's most important infrastructure projects by 2019-2020. The tunnel cross-section includes a utility and drainage channel at the base, with excavation materials compacted along the walls. Following the installation of utility corridors and benchings, the tunnel was prepared for pavement installation. The road structure comprises 2 gravel-based foundation layers, formation and fine planning, followed by 4 asphalt layers. These consist of an 8 cm thick formation layer, an 8 cm load-bearing layer, an 8 cm binder course, and a 3 cm wearing course. The quality and composition of the asphalt improve from bottom to top, with decreasing percentages of recycled material toward the surface. The gravel foundation provides a level subgrade and functions as a non-rigid base layer for the asphalt system. Installation equipment operates using a preloaded 3D model of the pavement profile, with real-time measurement feedback allowing installation to within 25 mm accuracy. Load-bearing capacity tests conducted after compaction revealed structural performance up to 30% above the required specification. The fine grading layer, between 3 and 6 centimeters thick, is installed using a precision asphalt paver. It compensates for any irregularities in the foundation layer, achieving a vertical deviation of no more than 5 millimeters. After rolling, its upper surface is situated exactly 27 centimeters below the final road elevation, ensuring precise depth for subsequent asphalt layers. Asphalt installation was meticulously pre-planned, with all construction geometries, daily production targets, and logistical parameters modeled in detail. Cloud-based systems coordinated the delivery schedules, asphalt quantities, truck cycles, and time-sensitive metrics. The 2 primary machines, a material transfer vehicle, MTV, and the asphalt paver, operate in synchronized sequence. The MTV, with a 45-ton capacity, buffers delivery fluctuations and prevents direct truck contact with the paver. It transfers asphalt via conveyor to remix the material and maintain homogeneity. A mechanical guide ensures the paver remains centered in the tunnel, while infrared sensors adjust the 11-meter-wide screed's height to millimeter precision using reference points on the side benching. Real-time monitoring records critical values such as layer thickness, tonnage placed, and surface temperature. Approximately 250 to 300 tons of asphalt are installed per 120 meters of pavement per hour. Each paving team operates under strict coordination to avoid machine stoppages, as any interruption negatively impacts the uniformity of the asphalt mat. The delivery fleet is continuously tracked via mobile applications, and real-time data sharing between the mixing plant and the job site ensures timely decision-making. Paving is conducted exclusively at night to reduce the risk of transport delays due to daytime traffic. The bituminous base course installation spanned 6 nights and required 7,500 tons of asphalt. Prior to placing each new layer, bitumen emulsion is sprayed to ensure proper interlayer bonding. The 8 cm thick load-bearing and binder courses were also installed in 6-night sequences following similar procedures, but with higher quality asphalt and reduced recycled content. Compaction is critical for layer performance. The vibrating screed achieves initial compaction of around 85%, followed by a first roller pass of 3 tandem vibratory rollers, increasing it to 95%. A second roller train further densifies to 100%, and final smoothing is performed by a non-vibratory tandem roller train. Continuous compaction measurement and documentation allow roller operators to optimize passes in real time. The final 3 cm wearing course was completed over 2 nights. For a seamless connection, the previous stage's edge was milled cleanly. The high-precision paving train executed the final pass with millimeter-level accuracy, integrating the transition with minimal visible joints. All work was completed in 18 nights across 38 centimeters of total pavement structure. The tunnel was officially handed over in November 2021 and became operational in 2022. Custom drums from curb roller manufacturing streamlined complex concrete work like drainage ditches by enabling single-pour precision. Crews save time and labor, no longer needing to monitor weather or match section angles across multiple days. These drums deliver consistent, spec-accurate profiles with no low spots or uneven edges. Redundant cross-forming is eliminated, freeing teams to focus on additional tasks. Built to exact project requirements, custom drums ensure reliable, uniform results, every pour, every time. Efficient, accurate, and tailored to your job. Atlas Concrete performed slip forming of a single-slope median barrier along the Belt Parkway NY using the Miller M-8800 machine. The project, executed for Mill Basin constructors, involved continuous concrete placement with precision shaping. The M-8800 ensured high production rates, uniform profile, and minimized joints, ideal for highway-grade safety barrier installation in tight urban corridors. The Charlestown wind turbine is part of a broader MWRA strategy that integrates wind, solar, hydroelectric, and biogas energy sources. Altogether, MWRA currently utilizes nearly 14 megawatts of renewable power, with an additional 3.7 megawatts under construction. At its Deer Island wastewater treatment plant, the authority self-generates about 23% of the facility's electricity needs. By capturing and utilizing methane gas produced during the sewage treatment process, MWRA meets more than 50% of the plant's total energy demand. The installation phase began with geotechnical surveys and foundation design, tailored to support the turbine's massive tower and nacelle. A deep concrete foundation was poured and cured, incorporating extensive reinforcement to handle dynamic loads from wind forces. Once complete, tower segments were delivered and assembled vertically using a 500-ton crawler crane, section by section under tight safety controls. The nacelle, housing the generator and gearbox, was hoisted and secured at nearly 270 feet. Next, the rotor hub and 3 120-foot blades were mounted. Each blade was carefully lifted and bolted into place under favorable wind conditions. Electrical systems were connected, including step-up transformers and net metering interfaces, integrating the turbine into MWRA's grid. Final testing and commissioning ensured performance benchmarks were met before entering service. This turbine complements MWRA's growing renewables, including solar, hydro, and biogas. With 14 megawatts installed capacity and 3.7 megawatts underway, sites like Deer Island already meet 23% of electrical demand, with methane recovery covering over 50% of total energy needs. The Charlestown turbine showcases both engineering precision and public investment in sustainable infrastructure. This comprehensive approach to renewable energy not only reduces operational costs and carbon emissions, but also supports long-term energy security for Massachusetts water infrastructure. The Charlestown wind turbine, in particular, exemplifies successful public investment in clean energy technology and is a key component of MWRA's evolving energy portfolio. The construction of the Elizabeth Quay Bridge in Perth involved complex engineering and precise execution. Designed as a suspension-style, double-arched pedestrian and cyclist bridge, the structure spans the inlet with two sweeping steel arches that cross each other diagonally. SRG Global was responsible for heavy lifting and structural assembly, capturing the entire process with dramatic aerial footage. Key phases included piling for the abutments, prefabrication of steel sections off-site, and transporting them via barge to the site. The 22-meter-high arches were lifted into place using strand jacks and temporary supports before being tensioned with suspension cables. The deck was incrementally installed between the arches, ensuring load balance throughout the build. The bridge not only serves as a key pedestrian route, but also symbolizes engineering excellence and urban integration within the Elizabeth Quay development. As part of the N40 South Ring Road flyover scheme at Sarsfield Roundabout in Cork, 18 precast concrete beams, each over 39 meters long and weighing up to 105 tons, were successfully installed during 2 consecutive night shifts. The operation utilized both a 350-ton and a 500-ton mobile crane supplied by CHL, ensuring safe and efficient lifting. Traffic diversions were in place to facilitate the works and ensure public safety. Beam placement commenced under strict time constraints and precise coordination. By 6 a.m. on Thursday, April 11th, all 18 beams had been securely positioned, marking a critical milestone in the flyover construction phase of this major infrastructure project. The construction of the Ravine Bridge involved precise assembly of 2 main arch segments. Arch 01 was lifted and positioned using multiple cranes, including a 200-ton, 400-ton, 1,600-ton, and 220-ton capacity cranes, with segments measuring up to 110 meters and weighing a total of 120 tons. After securing Arch 01, Arch 02 was assembled and stabilized in place. Expansion concrete was poured into Arch 02 to ensure structural continuity and load transfer between segments. The floor beams were installed subsequently, consisting of 4 spans with weights ranging from 32.5 to 112 tons per beam. Floor beams 01 and 02 each weighing 32.5 tons, were installed on spans 4 and 3 respectively. The largest floor beams, weighing 112 and 95 tons, were installed on spans 1 and 2. The precise coordination of heavy lifting equipment and staged concrete pouring ensured structural integrity throughout the assembly process. The construction of the Embalse de Contreras Viaduct del Cabriel section involved complex technical procedures across tunnels, viaducts, and a major arch bridge. Tunnel excavation used conventional drilling and blasting, with reinforced concrete lining. For viaduct piers, hollow section shafts were erected using self-climbing formwork in 4 to 5 meters lifts. Decks were constructed with pre-stressed concrete, utilizing either porticoed falsework or self-launching formwork girders. Reinforcement cages and tendons were installed before two-phase concrete casting. Next, the 830 meters Viaducto del Humo employed continuous cantilever casting with weekly segment cycles. The 261 meters concrete arch over the reservoir was built using a movable formwork carriage on cantilevered segments, stabilized with temporary stay cables anchored to a steel pylon. Each 3 meters arch segment was poured in 2 phases to control deformation. Hydraulic jacks were used to release the arch from temporary supports, followed by dismantling of auxiliary piers and completion of the upper deck on shored formwork. Load testing concluded the process. The installation of AAC, autoclaved aerated concrete, blocks by GreenCon, follows a standardized 22-course procedure, ensuring structural integrity, dimensional accuracy, and adherence to manufacturer specifications. The process begins with Course 1, marking, where layouts are drawn based on block dimensions. Course 2 introduces a string line to guide horizontal alignment. Course 3 involves laying a damp-proof course, DPC, to prevent moisture ingress from the foundation. In Course 4, thin joint mortar is mixed, using 31% or 14.4 liters of water per bag, ensuring optimal consistency. Course 5 establishes the leveling course, followed by Course 6, where excess mortar is removed to maintain clean surfaces. Course 7 entails the consistent application of thin mortar using a notched trowel. Course 8 requires precise cutting of blocks with a saw or power cutter. At Course 9, steel brackets are fixed every 600 millimeters to reinforce wall stability. Course 10 covers interlocking techniques at wall junctions. In Course 11, door frames are pre-set before block placement. Courses 12 to 14 include filling voids with cement sand mortar and installing frame ties per manufacturer's guidelines. Course 15 integrates door and window frames, while Course 16 involves stiffener columns and lintels as per GreenCon manuals. Course 17 details electrical/mechanical chasing. Course 18 involves refilling chases with cement sand mortar. Course 19 applies ALC render, 10 to 15 millimeters for external walls. Course 20 installs fiber mesh around door and window perimeters. Course 21 completes internal walls using a base coat, 4 to 6 millimeters, and finish coat, 1 to 2 millimeters. Course 22 addresses fixing details as per the official GreenCon fixing proposal. Trailing suction hopper dredgers, TSHDs, are ocean-going vessels used for dredging operations such as port maintenance, land reclamation, and coastal defense. They feature one or two suction pipes with drag heads that lower to the seabed. As the vessel slowly moves, sand and silt are vacuumed into the hopper. Once full, the dredged material can be discharged via bottom doors, rainbowing through a bow nozzle or pumped ashore using pipelines. Precision in placement is achieved by careful vessel positioning. TSHDs are vital in shaping and maintaining marine infrastructure globally.
Diameter Baisha Dam features 4,500 megawatts power capacity, 8.10 MAF water storage, dual diversion tunnels, diversion canal, right bank power intake, downstream permanent bridge, aggregate and batching plants, left abutment, relocated KKH, with continuous round-the-clock construction. At Gotthard Tunnel Section 242, workers drill boreholes using jumbo machines, load explosives, and secure the area with blast mats. Controlled blasting clears rock, with safety measures monitoring vibrations and emissions. Excavated material is tested and either reused or disposed of based on contamination levels. Baihetan Dam, located on the Jinsha River between Sichuan and Yunnan, is the world's largest arch dam. With a total capacity of 16 gigawatts, it is 7.5 times larger than Hoover Dam. Conmix Limited, a Bukatir Group company in the UAE, specializes in ready-mixed concrete and construction chemicals. From April 13 to 16, 2017, CONMIX set a Guinness World Record by continuously pouring 20,246 cubic meters of concrete for the Safari Mall in Sharjah. The operation involved 4 batching plants, 133 transit mixers, 16 mobile pumps, and over 230 employees working non-stop. This achievement showcased CONMIX's advanced production capacity, teamwork, and commitment to delivering high-quality concrete efficiently. A laser screed operates by using a rotating laser transmitter to establish a precise reference elevation. The screed machine is equipped with laser receivers that detect the laser beam and automatically adjust the height of the screed blade in real time. This continuous adjustment ensures the concrete surface is leveled accurately and uniformly. The process improves flatness, reduces manual labor, and increases efficiency in concrete paving projects. This video provides an overview of Record Holtzman's various ceiling edge formworks made from wood concrete, XPS, and EPS, demonstrating how quickly and easily the different versions can be installed. Depending on the masonry type, the L-shaped formwork elements are simply glued using low-expansion mounting foam or nailed in place. Record ceiling edge formworks serve as permanent formwork and are available in many sizes, heights, and custom dimensions. The typically 4 mm thick fiber cement base offers high compressive strength of 35 N per square millimeter. Options include formworks with a wood concrete base or mounting brackets for secure attachment. Key advantages include fast installation, effective bridging of uneven surfaces, no need to glue joints due to tongue and groove design, straight alignment, no stripping or removal, no cleaning required, and no release agents necessary. The Thermo and Neo versions allow forming and insulating in a single step. Surface preparation requires a dust-free, clean substrate free from mortar residues, with pre-wetting recommended for masonry in hot conditions, and no standing water on the surface. For fixing, apply a finger-thick layer of record mounting foam, wait 2 to 3 minutes for expansion, then press the element into place. On full-surface masonry such as aerated concrete, additional weighting or nailing is recommended. Formworks with a fiber concrete base or mounting brackets can be nailed with steel nails or shot nailed. During concreting, avoid pouring directly against the formwork. Instead, use a screed to pull concrete along the edge with a vibrator at approximately 35 centimeters distance. For formworks over 20 centimeters in height, secure them firmly and pour concrete in stages if height exceeds 30 centimeters. Precast roof slab erection involves lifting and positioning factory-made concrete slabs using cranes. Slabs are carefully aligned and secured to structural supports, ensuring rapid installation, improved quality control, and minimized on-site labor for faster and safer roof construction. The longest HDD crossing in Malaysia involved replacing a subsea potable water main between Pulau Indah and Pulau Kelang. The original pipeline, installed in 1992 by conventional dredging, suffered multiple leakages causing supply disruptions and high maintenance costs. HDD was selected for its cost-effectiveness and minimal environmental impact, reducing soil excavation from 785,000 cubic meters to only 894 cubic meters. The project installed a 5,850-meter, 406 millimeters diameter steel pipeline beneath the Strait of Kelang at a minimum depth of 16 meters. Installation comprised 4 stages: wash pipe and conductor casing installation, 311 millimeter pilot hole drilling, progressive reaming to 762 millimeters, and pipe pulling. This method ensured pipeline protection from seabed disturbances and anchoring hazards while maintaining ecological balance. The old Victorian brick sewer runs along Brighton's seafront, presenting a significant challenge during the construction of the new Brighton 1 360 tower on the site of the former Brighton West Pier. Because the original sewer line passed directly through the planned location of the tower's massive foundations, it was necessary to divert the sewer to enable safe and uninterrupted construction work. This project involved C.J. Thorne and Company Limited, based in Uckfield, East Sussex, who were responsible for carefully cutting into the old brick sewer and redirecting the flow. The team diverted the wastewater into a new, larger 1,600 millimeter diameter concrete sewer pipe. This new sewer was strategically routed around the southern perimeter of the I-360 tower's foundations, ensuring that the structural integrity of both the sewer and the tower would be maintained. The diversion process required precise engineering to prevent disruption of the existing sewer flow while enabling construction activities to proceed without delay. The team had to ensure the old sewer was safely opened and sealed as the flow was transferred to the new pipeline. This approach minimized environmental impact and avoided potential flooding or sewage backups. The entire sewer diversion work was successfully completed in January 2015, allowing the Brighton 1 360 tower project to progress smoothly. The project showcases effective coordination between civil engineering teams and construction crews to manage complex underground infrastructure adjustments in urban environments. The construction of a mountain tunnel begins with drilling holes into the face of the rock using a drill jumbo. These holes are then filled with explosives and detonated to break the rock. In softer ground, mechanical excavation may be used instead. Muck from the blast is removed using wheel loaders and dump trucks. Immediately after excavation, shotcrete is sprayed to stabilize the surface. Steel support arches are installed, and rock bolts are drilled and grouted into place. Finally, waterproof sheets are applied, and concrete is cast using formwork to complete the tunnel lining, resulting in a fully formed tunnel structure. The shaft construction at Grosvenor Mine involved the installation of a 7.8-meter diameter vertical access shaft, utilizing advanced large-diameter drilling techniques tailored to challenging ground conditions. The project commenced with the formation of a 1,200 mm diameter hard/soft secant pile wall using a Bauer BG-28 rotary drilling rig. This secant wall served as a reinforced perimeter casing to ensure shaft stability during excavation and drilling, especially in mixed strata. Each secant pile was drilled and installed with precise alignment to form an interlocked circular retaining structure. Hard piles were reinforced and spaced alternately with softer concrete piles, offering both shear resistance and lateral stability. Upon completion of the secant wall, a reinforced concrete bearing slab was cast at surface level, anchoring the structure and providing a working platform for the subsequent shaft sinking operations. The shaft drilling phase was conducted using a CAH 500 reverse circulation drill head mounted on a Liebherr LR 885 crawler crane base. This configuration allowed for high-torque vertical shaft reaming within the confines of the secant wall. The CAH 500 employed a combination of rotary cutting and suction to efficiently extract spoil while maintaining a vertical alignment and minimizing wall damage. The process included pilot hole drilling, followed by progressive reaming cycles to the final 7.8-meter diameter. Throughout the excavation, shaft depth and geometry were continuously monitored using real-time instrumentation. Geotechnical data was logged and evaluated to inform adjustments in drill torque, feed pressure, and slurry control parameters. The pre-sink operation included installation of a temporary casing and guide structures, allowing for safe personnel access and initial lining works once the shaft reached design depth. Upon completion, a final 3D laser scan survey verified shaft dimensions, verticality, and alignment relative to site benchmarks. The project exemplified precision geotechnical engineering and integration of heavy equipment in constrained vertical construction, achieving successful delivery of a critical underground access structure at one of Queensland's major coal operations. The replacement of the Vollmarstein Valley Bridge involved complex demolition operations to remove the aging structure before new construction could begin. The bridge, part of the A1 Autobahn in Germany, required full dismantling due to structural deterioration and increased traffic demands. Demolition works began with the removal of the road surface and guardrails, followed by the step-by-step deconstruction of the superstructure using heavy-duty cranes, hydraulic shears, and cutting equipment. Segments of the concrete bridge deck and steel girders were carefully detached and lowered to the ground for recycling or disposal. Temporary supports and scaffolding were used to ensure safety during the process. Special attention was given to the stability of the surrounding infrastructure and environmental protection, particularly to avoid debris falling into the valley below. The demolition phase was executed under tight schedules to minimize traffic disruption and prepare for the rapid construction of the new bridge. Coordination between demolition experts, structural engineers, and local authorities was essential throughout the project. Once the old bridge was completely removed, work proceeded on the foundations and support piers of the new Talbrook, using modern construction techniques to meet current load and safety standards. K E M R O C K 140 is a cutting-edge solution for trenching and pipeline construction, featuring the patented KEMROC chain cutter attachment. Engineered for precision and efficiency, the EK140 enables accurate trenching in confined or urban environments with minimal surface disruption. Its robust design ensures reliable performance in a range of soil and rock conditions, making it ideal for sewer, cable, and utility installations. The chain cutter operates with high torque and cutting force, allowing clean, straight trench profiles and reducing the need for rework. This innovative technology enhances productivity while meeting stringent construction and safety standards in civil infrastructure projects. The Vogeli Super 3000-2 asphalt paver was deployed for the construction of a 4.7-kilometer section on the A10 Berliner Ring. The machine operated with a maximum paving width of 15.5 meters to lay both the asphalt binder and the asphalt wearing course. The entire section was completed within 4 paving days, demonstrating high efficiency and productivity. Material supply was managed continuously and reliably by the Montana 3000-2I offset feeder, which delivered asphalt mix consistently to the paver's hopper. The integrated sensor systems on both machines enabled near fully automated operation, ensuring precise control of material flow and paving width. Prior to paving, the surface was prepared and cleaned to ensure optimal bonding. During the paving process, the USB sensor guided the paver's steering automation system, maintaining accurate alignment along the design profile and minimizing deviations. Immediately following paving, a tandem roller was deployed for compaction. The roller performed multiple passes over the freshly laid asphalt. The paving process involved careful control of the screed temperature and material thickness, monitored through onboard sensors to achieve uniform layer thickness and surface smoothness. The combination of automatic controls and real-time adjustments improved overall compaction and ride quality. For this large-scale project, WMH Worwe supplied the world's largest paver to the Overman/Faber joint venture. This equipment choice enabled efficient handling of high volumes of asphalt, meeting strict quality and timeline requirements on this major infrastructure upgrade. The 550-ton girder transporter is actively employed on-site to handle the transport of massive precast bridge girders. Designed for heavy-duty operations, This self-propelled modular transporter, SPMT, features multiple hydraulic axles for even weight distribution and precise maneuverability. It is equipped with advanced suspension and steering systems to navigate tight curves and uneven terrain commonly found on large infrastructure projects. With its high payload capacity and real-time control system, the 550T transporter enables efficient and safe delivery of girders from casting yards to the erection front, minimizing handling time and ensuring structural components arrive intact and on schedule. Complex excavation, 6 meters deep foundations, micropiles, landslide mitigation, topographic surveys, suspended bridges, modular retaining walls, full route realignment. Bridge girder erection is a fundamental stage in bridge construction, involving the precise placement of large structural components that support the bridge deck. The process begins with the transportation of prefabricated girders from the manufacturing facility to the construction site. These girders are typically made of steel or pre-stressed concrete, designed to meet specific load and span requirements. At the site, heavy-duty cranes, such as crawler or tower cranes, are used to lift and position the girders onto prepared supports or piers. Before lifting, thorough inspections of the girder and lifting equipment ensure safety and reliability. The erection sequence follows detailed engineering plans to maintain structural stability throughout the process. Girders are carefully aligned using laser-guided systems or mechanical guides, then secured with temporary supports. Final fixing involves bolting or welding to connect girders firmly to the piers and adjacent components. During and after installation, precise surveying and dimensional checks confirm correct positioning. Once the girders are installed, workers proceed to install the bridge deck, typically using precast slabs or in-situ concrete. This integrated process ensures the bridge's load-bearing capacity and long-term durability. Safety protocols and environmental considerations are strictly followed to protect workers and minimize site impact during the erection phase. The deal beam shifter was used on the Indian Street Bridge project on August 8, 2012. Each beam placement took approximately 1 hour. With this system, Archer Western contractors could install up to 5 Florida I-beams per shift, significantly streamlining the construction sequence and enhancing overall bridge erection efficiency. China's first 8 megawatts offshore wind turbine has successfully entered full load operation, marking a major milestone in the nation's renewable energy development. Installed off the coast of Fujian province, the turbine features a rotor diameter of over 160 meters and advanced aerodynamic blade design for optimal performance. With a single unit capable of producing 24,000 kilowatt-hours per day, enough to power thousands of homes, the project demonstrates significant strides in offshore wind technology. The turbine's successful commissioning involved extensive testing, grid connection, and full power output validation under variable marine conditions. It represents a key step in China's green energy transition. In 2016, Freysinet executed several major structural works across Turkey. On the Halik Metro Crossing Bridge and the Third Bosphorus Bridge in Istanbul, Freysinet installed advanced stay cable systems. For the BJK Vodafone Arena Stadium, the company completed a complex big lift operation for the stadium roof. In Kayseri, cast-in-situ bridges were delivered for the municipality. Additionally, Freycinet performed seismic retrofitting at Maltepe University's Bibuyuk Hospital and used the balanced cantilever method for the Cézanne Viaduct. The Pola Arm Reformador was constructed using Damon's modular building strategy, allowing rapid assembly and integration across multiple sites. Hull sections were fabricated locally at Astomar 20 shipyard in Mexico under Damon's technical supervision. Damon supplied critical modules and supported Mexican engineers with training, quality assurance, and engineering expertise. Key components, including the bridge, propulsion systems, and combat modules, were pre-outfitted and installed with precision. The modular approach minimized build time while ensuring high quality and complexity. This collaborative process enabled efficient system integration and testing, culminating in the successful delivery of a fully equipped ocean patrol vessel to the Mexican Navy. The high-speed railway under construction between Tianshui and Zhongwei in northern China is a critical component of the country's rapidly expanding rail network. Designed for speeds of up to 250 kilometers per hour, the 140-kilometer Tianshui-Zhuhai line will significantly reduce travel time between the two cities to just 40 minutes and enable trips from Tianshui to Beijing in approximately 100 minutes, down from the current 6 hours. The rail line, scheduled for completion in 2025, also plays a strategic role in improving regional access to the 2022 Winter Olympics, co-hosted by Beijing and Zhangjiakou. At the construction site, automated track laying systems such as the CPT 500 are being used. This machine integrates a rail pulling unit, a power engine module, and a transport chain comprising 37 flat cars that carry steel rails and concrete sleepers. The CPT 500 can lay over 2 kilometers of track per day using 500-meter-long continuously welded rails, each produced by joining 5 100-meter sections using seamless welding technology. These rails are then transported and positioned onto the concrete sleepers by robotic cranes that operate along the entire length of the laying machine. Once aligned, workers manually tighten the fasteners to secure the rails. Unlike traditional ballasted tracks, the new line utilizes ballastless slab track systems, which provide reduced maintenance needs and improve stability at high speeds. Track installation is followed by ballast tamping, precision alignment, thermal expansion calibration, and dynamic inspection procedures to ensure operational safety and passenger comfort. The mechanization of track laying has significantly reduced labor requirements, cutting the workforce needed for laying 500 meters of track from 100 to just 10 technicians, while tripling daily productivity. As part of China's 8 vertical and 8 horizontal high-speed rail grid, this project exemplifies the nation's ongoing commitment to rail infrastructure, with 3,500 kilometers of new high-speed lines planned in 2025 alone, contributing to a projected total of 38,000 kilometers by that year. This is a close view of the tilt-up construction process, where a large concrete panel, previously cast on-site, is being lifted into vertical position using a crane. The panel is rigged with lifting inserts and guided carefully by the crew to align with its designated position on the slab. Once upright, temporary braces are installed to stabilize the panel until structural connections are completed. Openings for doors or windows are pre-formed in the panel. This efficient and economical method allows for rapid construction of durable, load-bearing concrete walls in commercial and industrial building projects. The construction of the mother-child house in Niedergrünstedt near Weimar exemplifies an efficient timber building process completed in just 3 working days. The structure was built entirely using prefabricated solid timber wall and ceiling elements, with thicknesses ranging from 8.5 to 15 centimeters. The building components were pre-cut off-site, delivered to the site, and rapidly assembled using crane-assisted positioning and precise jointing methods. The walls were erected directly from transportation trucks in a sequence that allowed for immediate structural stabilization. Once the timber shell was in place, the team installed roof trusses and the anthracite-colored tiled roof, concealing gutters and downpipes behind vertical larch cladding for a clean finish. The thermal envelope was formed by adding 20 centimeters of insulation and a ventilated wooden facade. Large format windows were inserted on the south and west sides to optimize solar gain. Internally, the untreated and white glazed wood walls remained visible, showcasing the honest expression of material and craftsmanship. Integration of solar thermal connection and district heating occurred in parallel with the fit-out. Custom furniture, made from leftover cutouts of door and window sections, was installed as part of the final interior works. The construction process of the 47 square meters Habitera affordable house, costing approximately $2,500 USD, begins with site preparation, clearing and leveling the ground, and marking the foundation layout. A simple concrete footing is poured to support the structure. The walls are then built manually using interlocking Habitera blocks, which require no heavy equipment or skilled labor, and electrical and plumbing systems are installed directly into the structure. Each of the 2,568 blocks, costing about 50 cents per unit, is stacked in a line to form a stable, load-bearing wall system. Surface leveling, joint treatment, and structural inspection follow to ensure durability. Final finishing includes plastering or protective coatings, depending on local conditions. The entire process can be completed in just 14 hours, making it ideal for low-resource environments.